Welcome back to the third section of Chapter 2. In this section, we'll be looking at graphing linear functions. We'll be telling whether or not they're linear, and then graphing them using a variety of different starting points. First, our learning targets. I can determine whether a function is linear. It's important before you start graphing a linear function to know that it's actually a line. And I can graph a linear function given 2 points, a table, an equation, or a point and a slope. So these are the different possibilities. We can have 2 points, a table, which is really just a bunch of points, an equation, or point and slope. So first we want to see, is it linear? So telling her whether or not it's linear, we're going to be starting out with a table. Sometimes the tables can be sideways like this. They could also go up and down. It doesn't matter. What we're going to be looking for, though, is the distances between the x values and the distances between the y values, the f of x values. So the distance here from 2 to 5, we're just adding 3. And from 5 to 8, adding 3. 8 to 11, adding 3. So we're always adding 3 going up. This is something that gets to be important later on in further chapters. In this chapter, it doesn't actually make a difference that we're going up by the same amount. And then looking at the y values, from 9 to 17 is plus 8, 17 to 25 is plus 8, and 25 to 33 is plus 8. Hey look, all of these are the same, all of these are the same. That does mean that it's going to be linear. However, that's not all we look at for linear. Instead of just looking at whether or not they're the same, we look at the ratio between them. How much does y change divided by how much does x change. So in the first case, it's 8 over 3. Then it's 8 over 3, 8 over 3. Being that these are all the same, and these are all the same, yes, these are all 8 over 3. But this would be the change in y divided by the change in x, and that is the slope. And so if we were using this to write the equation of a line, which is not quite yet, but it will be coming up soon, that is how we would find the slope. Just do the change in y divided by the change in x. So let's look at another one. Here, we go from 3 to 9, which is plus 6. From 9 to 15 is plus 6. And from 15 to 21 is plus 6. We can look at the y values. 1 to 4 is plus 3. 4 to 10 is plus 6. 10 to 19 is plus 9. Are those the same? No, they are not. Yes, they do go up in a pattern, but that does not matter. They need to be the same. I don't know how many times people get like plus 1, plus 2, plus 3. Hey, they're all the same. They're all going up by 1. No, it's plus 1, plus 2, plus 3. And so these are not the same. And so it won't be linear. But again, let's look at the slope. 3 over 6, 6 over 6, and 9 over 6. Those are not the same. So it's not linear. And so that's how you can tell if things are linear or not. Being that we look at the ratio, these could be going up by different amounts. Like say here, we could be missing this middle term, and so we'd go from 2 to 8 is plus 6, and from 9 to 25 is plus 16. So we'd have 16 over 6, which reduces to 8 over 3. So that's whether or not it's linear. Now graphing. We're going to graph functions using a few different things. First, we can start out with a slope and a point. Actually, before we even get to slope and a point, if we have 2 points or a table, you can put the points on the graph and then connect the dots with a line. I'm not even going to show you that. Point, point, connect the dots. If we have a slope and a point, say the slope is 5 halves and it passes through 0, 2, we can graph this. We need a graph. Mine goes from negative 5 to 5, negative 5 to 5. Yours could be bigger depending on the problem. This is the graphic I had available, and so I specifically made questions that work on this particular graph. So we have a slope and a point. We need to know which one to use first, and that would be the point. The slope is a direction. Directions, you need a starting point for a direction. For instance, how do you get to Arlington? Well, you go southeast. From Stanford High School, you go southeast. If we were in Everett, you wouldn't go southeast. If you went southeast, you'd get somewhere completely different. So a starting point is important. That's where we start. So we're starting at the point 0, 2. So we can plot the point 0, 2. And the slope tells us to go up 5 over 2. So we go up 5, 1, 2, 3, 4, 5 over 2. And so somewhere out in here, that's off my graph. Instead of going up 5 and over 2, we could go backwards. We can go down 5 and backwards 2 to get the point right there at -2, -3. From here, we have 2 points. We can connect the dots, extend the line with arrows. It doesn't just go from point to point. Extend the line, put arrows on the end. Lines are infinite. Let's look at another one. A slope of 2 passing through the point -3, -4. So we start out with our point, -3, -4, and slope of 2. Well, this slope is a fraction, which rise over run. 2 as a fraction would be 2 over 1. We're going to go up 2 over 1, up 2 over 1. So we go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Is that a little bit of overkill on the number of points I have? Possibly. But it helps to draw the line, connect the dots, extend the line, arrows on the end, and you're good to go. If we want to graph lines using intercepts, we can do that. We'll find our 2 points, which happen to be intercepts. From here, we'll start out with an equation. The equation is just 3x plus 4y equals 12 for this case. Now, the fun thing about intercepts is we generally have 2 of them. If it goes through the origin, there's only 1 intercept. You can't really use the intercept to graph. But usually we have 2 of them. One of them is going to be 0, something. One of them is going to be something, 0. If it's 0, something, x is 0. So we plug in 0 for x. 3 times 0 is 0, so that term just kind of goes away. We have 4y equals 12. So what does y equal? Well, divide by 4, y equals 3. Same thing for the y-intercept. When y equals 0, that just kind of goes away. We have 3x equals 12, which means x equals 4. We have 2 points. We can graph them. We have the point 0, 3 and the point 4, 0. Connect the dots, extend the lines, arrows, and we're done. So if you just had 2 points, that's how you do it. Graph 1 point, graph a second point. It doesn't have to be on the axes. And extend. If you have a table, you can just pick 2 points and graph them. Or you can graph the whole table. So let's look at another intercept question. X minus 2y equals 5. So again, we're going to have 0, something and something, 0. If we have 0, something, that x value becomes 0. We have negative 2y equals 5. We can divide by negative 2 to get y equals negative 5 halves. People freak out with fractions. This is just negative 2.5. There's nothing funny. It's halfway in between negative 2 and negative 3. People confuse it for the slope, and they try and do weird, crazy stuff with it. Don't. It's just a number. And we can do the same thing for the other intercept. We can plug 0 in for y, so that negative 2 times 0 just becomes 0, goes away. And we get x equals 5. So we can get our graph, plot our 2 points, 0, negative 5 halves. See, it's just between negative 2 and negative 3. 5, 0. Connect the dots, extend the line, arrows, and we're good. So that's it, graphing using intercepts. If your equation is in standard form, where it looks kind of like this, something x plus something y equals a number, intercepts are a good way to go. Another way is writing it in slope-intercept form. What is slope-intercept form? You guys know it. If I told you to write the equation of a line, or asked you what is the equation of a line, what's going through your head right now is probably y equals mx plus b. That's slope-intercept form, where m is the slope, and b is the y-intercept. That's why it's called slope-intercept form. And so if we have one like this, it's in standard form. we need to make it y equals mx plus b. So we have to solve for y. First step, subtract the 2x, because we want to get y by itself. So we have negative 5y still equals negative 2x minus 6. And then divide by negative 5. So the negative makes these positive. 2/5, 6/5. Is this one pretty? No, not at all. It's amazingly ugly, but that's okay. It doesn't matter. We have a point, the y-intercept, 6/5, and we have a slope, 2/5. So we start out with our graph. The point, 6/5. It's just 1.2. It's a little bit over 1. And now, to get our points, we go up 2 over 5. So from a little bit over 1, we go to a little bit over 3. And then over 5. And we get our point. We could do the same thing going down. 1, 2, and over 5 to get over here. See how that makes a nice straight line? Connect the dots, extend the line, put arrows, and we're done. Even though the number wasn't a nice, pretty number to work with, we can still do this. How about if we have something like negative y equals negative 8x? Well, just multiply by negative 1. Y equals 8x. So we can start out with our graph. What's the y-intercept? Y equals 8x plus 0. So the intercept is at the origin. It's always there watching. And then the slope, 8. So we're going up 8 over 1. I'll put it up here somewhere. What if I only went over half? How far would I go up if I only went over 1/2? 4. Because that's half of 8. So we go up 4 over 1/2, up another 4 over 1/2. That gets us our 8 over 1. Connect the dots, arrows, extend the lines, and it's a little bit of magic. Finally, we're going to be looking at vertical and horizontal lines. Vertical and horizontal lines look like things like x equals 3 or y equals negative 2. Now the question is which is which? Well, if we have x equals 3, that means x equals 3 no matter what y equals, which means that's a vertical line. And y equals negative 2 means y equals negative 2 no matter what x equals. It's a horizontal line. So they kind of switch from what you think that they would be. Usually you see x equals, you think horizontal, but it is actually vertical. Also, fun thing about x equals, a vertical line, is it's the only line that's not actually a function because it does not pass the vertical line test. You push the button on the soda machine. It only has one button. You push it, you get out something. It could be anything. You never know. And so that one doesn't work out as a function. But we can still graph it. Also, it's the one that can't be written as y equals something because it's x equals something. So x equals 3. Start with the graph. Just go to an x equals 3 here, x equals 3 here, x equals 3 here. X just equals 3, and so we just draw a vertical line at x equals 3. And then horizontal, y equals negative 2 means, well, this is when y equals negative 2, and it doesn't matter what x equals, so our horizontal line goes at negative 2. And that's it. So lots and lots of graphing functions today using a variety of different methods. A lot of these methods you can use any of the methods for a lot of different problems. Sometimes one is easier than the other. In this section, it'll tell you which method to use, so you don't have to make that choice. But other than that, I will see you next time for writing linear functions. Until then.